Okay, so let's start. Okay, a few announcements that you can see there. So what's important about homework 4 is that we will not give the extension that you have by default, the 4 days. And the reason is it's due on Thursday. The midterm exam is the Tuesday after it. And we want to be able to give the solutions in time for you to...
I'm not getting your mic. Can you...
You're not.
Is it on?
It's on.
Okay, can you put it up higher on your shirt?
Okay. Can you hear me up there? Okay, can you hear me? Okay. So, anyhow, so please take this into account. You have a week from today, but no extensions this time. Midterm, next Tuesday, the 27th. So we are going to put some recent midterm exams on the web tomorrow, so you'll have a chance to look at it. Basically, it's in class, 75 minutes, about 4 questions, closed books. So don't bring anything with you. Questions? No questions. Okay. And finally, yeah, question.
Is the midterm going to include neural networks?
Everything that we've covered until next Thursday, until the lecture before the exam. I'm going to spend a short time next Thursday overviewing, kind of reminding you what the exam is about, but you should know. I mean, all the lecture notes are out. So basically all the material that we covered. You don't have to, if you're worried about it, you don't have to memorize too many formulas. You have to understand the principles. If there is going to be any important formula, we're going to put it at the back of the exam. So hopefully try to evaluate your understanding of what we've done so far. But I'm going to talk more about it on Thursday. If you do have questions, ask. Finally, project proposal due tomorrow. So it's going to be on Compass, or you submit through Compass. And we're also going to ask you to do some peer review. If you want to, you don't have to. I think it will be interesting for you to see also what other proposals people have written. Okay. Questions? Okay, so let's start. So I want to recap where we are. We've talked a lot about algorithms from decision tree through linear classification, perceptron, we know variations, gradient descent, or at least one aspect of gradient descent. We're going to see more of gradient descent. Last week you talked about neural networks, so you've seen gradient descent again. And you talked about 2 important things. One is just backpropagation, sort of the basic algorithm. And you talked also about convolutional neural networks. So I'm not going to continue. There is a little bit more material in the slides on recursive neural network, but I'm not going to continue with it because I want to move forward. Really, if you want to read about recursive neural network in the lecture notes, the basic thing is you know backpropagation. So it's the same principle. The architecture is different, but the learning rule is the same learning rule. So that's going to be important. So we talked a lot about algorithms. We talked about theory. So 2 types of theories we've developed. One, mistake bound. So we talked about how to analyze algorithms from the perspective of mistake bound. And we then talked about pack learning. So we have a framework within which we can actually define learnability. You know, what does it mean to be learnable? And what does it mean to not be learnable, and we understand generalization as a function of this. So you know something about how will the algorithm do in the future as a function of different complexity parameters. Most importantly, you know how it depends on the hypothesis class, the size of the hypothesis class, or more generally, the VC dimension of the hypothesis class, and a few other complexity parameters. So that's basically what we've done so far. And now I want to go back to algorithms. And one of the interesting perspectives is, so beyond understanding of learnability and generalization, is there any other, are there any other implications of the theory? And it turns out that, yes, you can actually develop algorithms and understand some algorithms really by questions that are driven by theory. And that's actually what we're going to talk about today. We're going to talk about boosting. Questions about this? Okay. So algorithmic implication of the theory. So boosting today is viewed as really a general learning paradigms. Okay. That allows you to put together a strong learner given a collection, could be a very large collection of weak learners. And we're going to formally define what I mean by weak learner. But intuitively, you should be able to, weak learner is a learner that isn't so good. So originally, the boosting algorithm was proposed as an answer to your theoretical questions about back learning, pretty much at the beginning of back learning in the late 80s. And the paper that Rob Shapiro wrote about it in '89, it's on the web, on the webpage of the class. It's still a very, very interesting algorithm, a paper to read. It has a lot more than just the first boosting algorithm. In particular, it gives some kind of deeper understanding of what does learning mean. For example, from the perspective of compression. So there are results that would say things like, if a concept class is efficiently pack learnable, then it is efficiently pack learnable by an algorithm whose required memory is bounded by something that is polynomial in the complexity parameter. So something about the size of the hypothesis. And moreover, it relates compression and learning in a very specific way. There is no concept class for which efficient pack learnability requires the entire sample to be contained in memory at one time. There is always another algorithm that forgets most of the sample. So really, learning is, in many respects, equivalent to compression. So these are just some byproduct of the boosting algorithm. We're not going to talk about it. We're going to talk about one boosting algorithm. In fact, the one algorithm that became practical, different than the original algorithm of Rob Shapiro, but very related. So really, beyond theory, the key contribution of boosting was a very practical algorithm that is used, not only by thousands of papers, but actually in a lot of systems. And as I said earlier in the semester, if you know little about your data and about what you're trying to learn, understanding of the concept you're trying to learn, boosting, possibly boosting of small decision trees would be the best kind of general purpose learning algorithm that you want to try to use. This is true even, I think, with the resurgence of neural networks, because it typically requires a lot less data than you need in neural networks. But anyhow, so boosting is a member of the family of ensemble algorithms, and I'm going to talk toward the end about other ensemble algorithms. But unlike other algorithms, boosting really has good theoretical support and stronger guarantees. So you can look at a demo, but I'm not going to touch it, but rather talk a little bit about give an example and talk about the theory of boosting and what kind of insight it gives us to understanding learning. Okay, so here is an example, a real example that was the first practical application, if you want, of boosting, a system that AT&T developed, I think in the late 90s or early 2000s. How may I help you? It's kind of old Siri, if you want. So really the goal was to take phone calls from customers and automatically categorize them and navigate them into people that can take care of it. So there's some text, and you want to classify it into collector number, calling card, billing credit, and so on. So the key observation of people that actually try to build a machine learning program to take the conversation, the phone conversation, and map it to the appropriate person to handle it was that it's very difficult to put together a robust classifier, but it's relatively easy to find rule of thumbs. Sort of very simple rules, if you want, classifiers that are often correct, but don't have a lot of coverage. So, for example, you could say, well, if I hear card, then it probably is calling card. But how to put this together to something that is global accurate prediction wasn't so simple. So this is where boosting comes in. So the boosting approach suggests to do the following thing. So you choose a small subset of examples and use it to derive a rule of thumb. Take another set of examples, use it to derive another rule of thumb, do it many times, and combine these learned rules into a single hypothesis. That's kind of a very high-level perspective of boosting. We're going to see that this selection, in fact, is a little bit more involved. But really, this kind of general approach brings up two questions. One is how to choose examples to focus on in each round, and two, how to combine. And these two actually turn out to be very, very important. So boosting is a general method that allows us to convert this rough rule of thumbs into a prediction rule, a classifier that is highly accurate. Okay, so really, how was it motivated? So we all remember, hopefully, what is pack learning. I'm going to call it now strong pack learning. So pack learning, here's the definition. For any distribution, for any epsilon and delta, small constants, as close as you want to 0, given polynomially many random examples, there is an algorithm that finds hypotheses with error less than epsilon and with confidence at least 1 minus delta. All right? So an algorithm that satisfies this is a pack learning algorithm. Now, we can weaken the conditions on epsilon and say that, you know, we can do this. I mean, you give me data, sample from any distribution, but all I can do is I can find a hypothesis that has epsilon that is a little bit below a half, bounded away from a half. All right? So if you want 0.49, yes, I can find something with error 0.49, but I cannot do it for any small epsilon. So that's maybe not good enough for you, right? Because you want a hypothesis that really will make small error. But we can define weak learnability, a weak pack algorithm, as an algorithm that can satisfy this. So again, for any distribution, given polynomially many random examples, it finds a hypothesis with error less than epsilon with high confidence, but this is going to be only 49%. So probably not enough in most practical applications. So the question that was asked in a paper by Kearns and Valiant was, let's assume that you have this algorithm. Can you boost it and get a strong pack learning algorithm from it? Saying it another way, does weak learnability imply strong learnability? And this was a problem that a few smart people try to answer. And actually had some evidence that maybe the answer is no. But you should know that this evidence isn't sufficient. So for example, what people were able to prove, this is actually part of Mike Kern's thesis, he showed that if you restrict pack learnability not to be for any distribution, but only over the uniform distribution, then the answer to this question is negative. That is, over the uniform distribution, weak learnability does not imply strong learnability. Saying it another way, so there could be a pack learning algorithm over the weak pack learning algorithm over the uniform distribution, but for the same class, there is no strong pack learning algorithm, okay, over the uniform distribution. Now, you should say, we already know that the distribution-free assumption is really important, right? We saw about a week ago, or 2 weeks ago, that this is crucial in other examples, right? When we transform the feature space, we saw that the free distribution assumption is really, really important. So maybe it's important also here, and this does not really mean that it's a negative result. And indeed, this was the case. So this is a negative result, but it's not for the general case. So in '89, Rob Shapiro developed the first boosting algorithm. The basic idea was to start with a weak learning algorithm, call the learning algorithm 3 times on slightly modified probability distributions, building on the free distribution assumption, and showing that you can combine these 3 learners and get a slight boost in accuracy. And then you can recurse and get to any epsilon that you want. A year later, Yoav Freund, also part of his PhD thesis, actually developed another boosting algorithm, conceptually simpler algorithm, that had similar guarantees. And then later on, a couple of years later, was the first kind of real application of boosting. This was done at AT&T, where they actually built a system that used boosting. A lot of practical issues limited really the applicativity of this. In '95, Freund and Shapiro developed together the AdaBoost algorithm, so adaptive boosting, a new version that in fact combine ideas from this and from this to an algorithm that we're going to present in a few minutes that really had strong practical advantages over various previous versions of boosting. And this really had kind of caused a small revolution in machine learning, because huge number of papers that actually showed that it's very practical, a lot of theoretical understanding in addition to the original theoretical understanding, and even today, still a very, very practical algorithm. So that's the history. Actually, there are a few interesting lessons here for PhD students. So one important lesson for you is that, so Yoav Freund actually developed boosting algorithm even though he knew that the problem has been solved already. So the fact that someone writes a paper on something, even if the paper is actually excellent, in this case, doesn't mean that everything is closed. You can still develop other approaches to something that eventually might have value. In this case, clearly had value. So that's lesson number 1. Don't be discouraged by the fact that someone has published on a problem that you think is important and that you have good ideas for. Lesson number 2 is this paper, the '95 paper, if you check, appeared in a rather esoteric conference. I think it was the European Computational Learning Theory conference, very small conference, because it was rejected for more major conferences. The reason it was rejected was because reviewers said, well, we've already solved the problem. You know, there is a paper about boosting, problem solved. This is just a simpler algorithm that solves the same problem. And I'm sure it was disappointing at that time, but eventually it got in somewhere else and had a lot of impact, a lot more than earlier boosting algorithms. So again, don't be discouraged if you believe that this is the right thing to do and it's good. Keep trying. So okay, so with these lessons, let's move on to talk about boosting. Questions so far? Okay, so what is really boosting? So my goal here is to define a formal algorithm and actually analyze it. And you will see that the analysis itself actually forces you to understand a lot of things, mostly definitions, but important definitions about learning. So let's start. So we're given a training set, M examples. We're going to assume that Y, the label, is plus or minus 1. And this is what boosting is going to do. For capital T rounds, we're going to construct a distribution, dt, on the M examples, 1 to M. We're going to find a weak hypothesis. Think about it as this simple rule of thumb, HT, with error epsilon t on this distribution dt. Right? So epsilon t is just the error. Remember the definition of error is just the probability that H is different than Y on this distribution that we care about. And we're going to do this capital T times, and at the end, output a final hypothesis that is going to be some combination of these hypotheses. Okay, so a little bit more detail. So we have to construct a distribution. We're going to start with the uniform distribution over M examples. So D1 is going to be just 1 over M. D1 of the ith example is 1 over M. And now we need to change the distribution. So given dt and ht, I'm going to define now what is dt plus 1. dt plus 1 is going to be dt. I'm going to split it first to two cases. A case where we predicted correctly on the ith example, and I'm going to tell you how I define dt plus 1 of I as a function of dt of I, and then the case where we made a mistake. So if we did not make a mistake, I'm going to take dt of I, multiply it by e to the minus alpha t, for some alpha that I'm going to define in a second, and then normalize by dividing by zt. If we did make a mistake, I'm going to do the same thing, only that I'm multiplying by e to the plus alpha t. Combining these two into one expression, dt plus 1 of I is dt of I normalized times e to the minus alpha t yi h of xi. Now remember that this is positive if we do not make a mistake, right? The sign of h and the sign of y are the same. Negative if we make a mistake, and therefore you get these two. Okay, so now zt, as I said, is just a normalization constant. So you can figure out how to write it down. We'll write it in a second. And alpha t I define as a function of epsilon. So alpha t is going to be this half ln of e to the minus epsilon divided by epsilon. So the first thing that you want to observe here is, what is the value of alpha t? At alpha t. What? Why would it be greater than 1? So epsilon is less than half, so 1 minus epsilon over epsilon is greater than 1. So this ratio is greater than 1, and therefore alpha t is is positive, right? Okay, so I should have stopped here first. How do I combine this? So notice that the way I combine the alpha t is the weighted sum of the hypotheses with alpha t's as coefficients. And now we're talking about this alpha t. So we agree that alpha t is going to be positive due to the weak learning assumption, right? So the weak learning assumption basically says epsilon t is bounded away below from a half, and therefore this ratio is greater than 1, this is positive, right? Which means, this is another way of writing it, so notice that e to the alpha t is the square root of 1 minus epsilon divided by epsilon, which we agreed is going to be greater than 1. And therefore, that means that if I made a mistake, I'm multiplying the distribution by something that is greater than 1. So the weight of the example on the new distribution goes up. And if I did not make a mistake, if I got it right, the weight of this example is going to go down, right? So I'm going to put more emphasis on those examples on which I made a mistake next time, right? And then I'm going to normalize, right? So because I want to make sure that this is still a distribution, dt plus 1. Okay, so when you look at this expression, one thing you want to think about is what's going to happen when I do this many times, right? So essentially, think about unwrapping all these products. So what's going to happen? I'm going to start with 1 over m, and then multiply repeatedly by this, by e to some power. I'm going to keep on doing it. Product of e to some power means it's going to be e to the sum of this. So it's going to be e to this sum. Okay, at the end. You see this? So that's one thing. The other thing you can think about, and we're going to go back to it later, is what is this z? What is this normalization factor? So what do I want? I want this to be a distribution, which means that when I'm taking this expression here, this defines dt plus 1 at the point I, and therefore if I sum it up over all i's, it should give me 1. Okay? And because when you sum it up over all I, it gives you 1, you can basically get zt out of there. It's going to be the sum of dt of I over all I times e to the minus alpha t yt, this expression. Okay? Basically by summing everything and requiring that it's 1. Okay, we're going to go back to this. Let's first look at this example. So this is what boosting is going to do. I'm given a data set. Originally, all the examples that I see here, 5 positive, 5 negative, are equal from my perspective. The distribution is 1 over 10. The weight of each one is 1 over 10. And I'm going to come up with H1, my first weak hypothesis. This is the first weak hypothesis. This line, to the left of it is positive, to the right of it is negative. So I made some mistakes, right? These 3 examples are mistakes. My error is epsilon 1 is 0.3, right? 3 out of 10. And if you do the math, alpha 1 is going to be something like 0.42. Okay, so what do I do now? I'm going to generate my next distribution, D2. In my next distribution, just a second, those examples on which I made a mistake are going to be heavier, right? So look at these 3 pluses. They are now bigger than these 3 pluses. All the others, doesn't matter whether they're negative or positive, all the other 7 examples I predicted correctly, so they're going to be lighter. And the sum, again, is going to be 1. Yes?
So is the H1 found just...
Okay, so good question. How did you find H1? So I didn't tell you how I found H1, but in principle, yes. So you have a new hypothesis, a hypothesis class. In this case, the hypothesis class I'm going to use is axis parallel separators, vertical or horizontal lines, and run a learning algorithm and find it. So in this case, basically, you're going to do a sweep left-right and a sweep top-down and find the best hypothesis you can find. In general, you can run, if you care about small decision trees, you will run your favorite decision tree algorithm and make sure that you find just small decision trees, like what you've done in the problem set. Okay, so now we have this new distribution, and now we are learning again. Now we're going to run the same algorithm. Why would we get a different hypothesis now? Because it's the same set of examples. Why would it be different? Right, so what has changed is really the distribution. And really you are driven by, I want to minimize the error. Right? This is what your learning algorithm tries to do. The error of a given hypothesis, let's say this, is going to be different here than it is here. Right? So this is why things change from one round to another. So now, actually, I'm going to find this hypothesis. This is my H2. To the right of it, I'm saying negative. To the left of it, I say positive. Notice that, again, I made these three mistakes. My epsilon is 0.21. Before, when I made three mistakes, my epsilon was 0.3 because it was over the uniform distribution. Now, three mistakes, but the error is different. Again, I'm not counting, but rather it's a distributional notion, right? What is the error over D2? This is what I'm trying to minimize. So in this case, epsilon 2 is going to be 0.21. And again, you compute your alpha 2. You probably expected it to be a little bit larger than alpha 1, right? The error goes down, the epsilon goes up. Sorry, the error goes down, the alpha goes up, right? Think about you want to weigh higher those hypotheses that are better, that have lower error. And again, I have this D3. And again, you can check these two examples that I got right, for example, become smaller. These three minuses become bigger. All the rest also becomes smaller. Okay? And this is my third hypothesis. Again, now it's this horizontal line. I made three mistakes. My error is even lower than before, even though it's, again, three mistakes. And my alpha is larger. And that's going to be enough. So my final hypothesis is a weighted sum of these three hypotheses that you can visualize this way. And you can see that in this case, this hypothesis makes no mistakes. Now, can I go on? Why did I stop now? Because there are no mistakes of the combined hypothesis. Can I go on?
Yes.
What would have happened if I go on? Okay, so one option here is it will stay the same. If I had H4 here, will the final hypothesis be the same? So notice that when I learn a hypothesis, going back to the first question, I run another learning algorithm. I run a learning algorithm that learns vertical and horizontal lines, right? So it still could be the case that my best horizontal or vertical line is going to make mistakes. What does not make a mistake is this combined hypothesis. But if you look at the data, it's very likely that a vertical or horizontal line is going to make a mistake. Which means that when I do sum over 4 hypotheses, it's going to be somewhat different than this. So, yeah.
So, do you have to modify your...
You mean the basic quick learning algorithm? Do I have to modify? Let's think about our basic learning algorithm just as an algorithm that sweeps over vertical or horizontal lines in some resolution, tries, sees what's the error, and decides, chooses the one that minimizes the error. Let's say your resolution here, let's say this is 0 to 1, so your resolution is 0.05. You have 20 hypotheses to try and 20 hypotheses, horizontal lines to try, and you figure out which one minimizes the error. So I don't change the algorithm, but every time, given that I'm running on a different distribution, the error that a given hypothesis will incur is going to be different, right? Just because the weight of each example is different. But the algorithm is doing the same thing, just stopping at a different place because the distribution has changed. Is that clear? So, okay, yeah.
So, looking at this one, I think there's a high bias here. I mean, is it good to have a high bias?
What do you mean? Who has an...
Exactly learning, which is like positive examples and negative examples. So, making no mistakes, right? So, if I now plot another point which is in the red region, which is a positive example, it will predict me. So, I think there is a high bias here.
Who has a high bias?
The learner.
The final hypothesis? As I said, you can keep on going. So the nice thing about boosting, I gave you a specific data set. And I decided to stop after 3 because we don't have time. But I could keep on going, right? So if there was another example here, first of all, it would have changed these also. But I can keep on going. Each one of the weak learners may make mistakes, even though the final hypothesis stopped making mistakes. And I'm going to keep improving the final hypothesis. At least I'm claiming that I'm going to keep improving. So the cool thing is that even though this one does not make mistakes, these could keep on making mistakes and eventually add to this final hypothesis. Now, I don't know until the next slide whether it's good to add more and more hypotheses, but I could add more and more hypotheses. It turns out that what we will show is that you can keep on going and you will only improve, right? So eventually, even if you invent a bad data set for this, I will probably be able to minimize error even on your bad data set.
So what I meant was like, it is doing good on testing, the training data set, but if you give a test data set, it won't do as good as on the training data set.
Okay, so keep this question for a second, and we'll address it in this slide, in fact, I think. Okay, so what do we know about? So this was running AdaBoost, and you can see that it's very simple. In fact, it's a 2-line code, given that you have the weak learners. And there was this observation that is interesting, but the question is, what can we say? Yes?
Just a small question. Like in the previous one, you said
Yeah.
so in our algorithm, after each
You can.
how else do you stop?
So you have to devise some stopping criteria. You can say, I'm going to run 1,000 times and only then start checking, right? So you will have to come up with some stopping criteria. Okay, so what can we say? So the theorem says this: run AdaBoost. Let's assume that epsilon t, the error in round t, is a half minus gamma t. I'm guaranteed that I can do this because the condition is that there is a weak learner, which means I can always do this. Then the claim of the theorem is that the training error of the final hypothesis is bounded by a product over t, the rounds, of this, 2 times square root of epsilon t minus 1 over epsilon t. So before we, just to understand the theorem, we're going to do a little bit of algebra. I claim that you can write this way. This is simple algebra, right? Because if you substitute for epsilon t this, then you will get quarter minus gamma t squared. So we get this with the 2 that is outside here. And in order to move from here to here, I'm basically using the fact that 1 minus x is less than e to the minus x. My x here is this. And therefore, what this theorem says is really that the training error is less than e to the sum over t. Now let's assume that for all t, this gamma t is greater than gamma. I can always do this, right? I'm going to take the t, the gamma t that is closest to 0, and call this gamma. Then the training error is less than e to the minus something positive times t, capital T, which is the number of rounds. 1 second. What did I show here? What does this show? Bounded is not good enough. What does it really show? As t increases, this guy goes to what? Goes to 0, right? Which means I can, if I increase t, the training error can go as low as I want. Right? So epsilon can go as low as I want. So I'm starting with a weak learner with an error that is just bounded away from a half, 0.49. And if I take enough weak hypotheses, capital T weak hypotheses, I can get error that is as low as I want. That's what it says. Okay? Question here.
What's the meaning of the gamma t, say, value between 0?
What does it mean?
What's the meaning of gamma t?
Gamma t is just a constant that I'm using here to show that the error is bounded away from a half. It cannot be exactly a half. It has to be bounded away from a half by some positive number.
So gamma t is around.
The error has to be always between 0 and 1/2. Otherwise, I don't have a weak learner. But it can be as close as you want, but bounded away by a constant from 1/2. 0.499 would work. You choose capital T. All I'm saying here is that if your capital T is large enough, you can get any epsilon that you want. So you can choose epsilon, and as a function of it, figure out what should be your capital T.
So capital T should be derived from.
No, capital T is the number of rounds that you run the algorithm. You run it capital T times. And what this theorem shows is the relation between capital T and the training error, the final training error. Okay, if you want a small training error, less than 0.01, figure out what should be your capital T. Maybe it should be 1,000. Okay, so we answered 2. What does the bound mean? Right? It basically means that we have a pack learning algorithm. And in practical terms, it basically means that we can get as low a training error as we want. What about 1? Why is the theorem stated in terms of minimizing the training error? Is that what we want? That addresses the question that you had. Why do I phrase it in terms of training error? Yes?
That's what we showed in using the VC.
Exactly. So basically, we actually proved a week and a half ago that that's good enough. If you, because of the VC dimension or Occam's razor result, what we showed is the relation between the training error and the test error, and the real error. And we said, because the VC dimension of this hypothesis class, it's really a linear function over H, over the class of weak hypotheses, because this is a low expressivity function class, if the training error is small, the test error is going to be small. So that's going to address your question, right? So don't worry. If you can do this, it's going to be OK also in the future. I'm not saying that you'll not make mistakes in the future, right? It's a probabilistic statement, right? It just says that with high probability, at least 1 minus delta, your error is going to be bounded away. It's going to be as small as you want. So that's why now, given that we have this pack learning theory, it's OK for us to prove the theorem only on the training error. Yes?
But is this not linear? IBC dimension, because
It's linear over a fixed set of hypotheses. What is this fixed set of hypotheses? You choose. What is the class of weak learners? It could be, if it will be the class of all decision trees, you're in trouble, because then the VC dimension is going to be large. But as a function of the class from which you've chosen H, you can bound the VC dimension. So for example, if I'm taking the example that I've shown with linear separators that are vertical, low VC dimension. If I'm taking linear separators in general, as H, also low VC dimension. If you take decision trees, not good. Okay? So, but it's all under your control, right? So you can control the expressivity of your function class, and therefore the gap between this training error and the test error that you'll incur. Okay? In practice, of course, people will use H's that are relatively simple. Doesn't have to be vertical or horizontal lines. Could be small decision trees of size, depth 2 or depth 3, which is really what people are doing in practice quite often. But the important thing is that you can control the expressivity of your class, and therefore, this is a good thing to prove. Questions? Okay, so actually I want to prove this for 2 reasons. One, because it's actually relatively simple, even though it seems very deep, and it is. And second, because it will force us to go to the definition and understand some of the key definitions that we should understand in learning. Okay, we already talked about this. Essentially, what this says that we care about this, right? We want to prove that the training error is less than the product over all t rounds of this epsilon 1 minus epsilon. The rest is just algebra, right? Which is shown here. Okay. Yeah, that's what I said. Okay, so say it again. Okay, so first of all, I'm claiming that I'm defining f of x to be this linear combination of h's, right? So this is your final the final function, and you're going to make predictions using the sign of f of x, positive or negative. Okay? Now, there are going to be 3 steps, and the first one is just unwrapping the recursion, which I hinted on before. So remember, what did we do? We defined a distribution, and in each round, the distribution was the previous distribution times this e to the minus alpha or e to the plus alpha. So now, what does it mean? It means that I started with 1 over m, uniform. Each I has 1 over m. And then I multiply by e to the alpha t. So now we're going to write this down, t times. And essentially, that's what we're going to get. We're going to get e to the sum. And every time we're dividing by another zt. So in the denominator, we're going to get the product of the zt's. So this is just writing the algebra. I'm writing it here in another way because I denoted this sum to be f of x. So that's what I have. 1 over m e to the minus yi f of xi divided by the product of the normalization factors. Now notice that this is basically the evaluation of f, the final function, on the ith example. And again, you can think about whether this could be either positive or negative, depending on whether you made a mistake on the ith example or not. Okay, so this is the final weight of the ith example. This is just algebra. This is our step 1. Step 2, I want to show that the training error is bounded by the product of all the normalization factors, the zt's. Again, let's remember that if the final hypothesis makes a mistake on example x, it means that y f of x is negative. Right? You know this? It means that e to the minus y f of x is greater than 1. We're going to use this. Okay, so what is the training error? And again, this is really why I'm doing it, because I want you to be able to write down the training error. What is the training error? The training error could be is an average over all examples of 1 and 0. 1 if I made a mistake, 0 if I did not make a mistake. And I'm averaging these over all the examples I and divide by m. Okay? Just a definition. Now, I'm claiming that I can bound these as follows. Why is this true? What I'm doing here is I'm basically using, okay, this is just the definition of training error. And in the inequality, I'm basically using this. E to the minus yi f of xi. If I made a mistake, this guy is always greater than 1. So I can take the 1 here in the sum and replace it by this, and it only goes up. And of course, I can replace the 0 by this. It's always positive. So this sum, which is the average of this sum, 1 over m, for all examples I, is greater than the final error. Okay? What does that mean? We can go to step 1 and see what did we prove here. That the distribution of the ith example is 1 over m, this ratio. So I'm just multiplying this, bring it to here, and I get this. So the training error is just the sum, the distribution, sum over all I, the distribution of I times the product of the zt's. And I'm arguing now that this is equal to the product of the zt's. Why is that? Yeah? Right. Because d final of I, sum over all I, it's a distribution, so it sums to 1, I just get z of t. Okay. So again, the key thing from your perspective beyond this algebra is to really understand the definitions and be able to write this down. Okay, so this is step 2. Step 3, I'm actually going to prove that ZT itself, the normalization factor, is this square root of epsilon over 1 minus epsilon. So again, we're going to go from the definition and remember that ZT is a normalization term. I'm going to go back to the first slide when I defined this. Where was it? Yeah, okay. So we define dt plus 1 this way, dt times something divided by zt. And from here, basically what you want to say is you can figure out what is an expression for zt. You just sum over all I, and you will get an expression from zt, which is this. Okay? Again, a little bit of algebra. So now let's go back and use it. Step 3. So zt is the sum over all I of dt of I times e to this prediction, weighted with alpha t. Now what I'm going to do is I'm going to split this to 2 terms. I have a sum here over all my examples. I'm going to split it to a sum over those examples on which I made a mistake and those examples on which I did not make a mistake. Okay? So now notice that in this sum, actually e to the alpha t can go outside of the sum. Right? What's inside the sum? What is the sum dt of I over all i's on which I made a mistake? What is this expression? That's my error, exactly, and that's very important for you to realize. So again, look at this expression. I took e to the alpha t outside. This is the sum of the weight of all the examples on which I made mistakes. This is exactly my error. Okay? And same thing here. I take e to the minus alpha t out of the sum. It doesn't depend on I, just a constant. And what I have here is the sum of the weights of all the examples which I got right. So this is 1 minus the error. Okay? Again, this is just definition. So I want you to understand this. So this is really the definition of the error, the way I move from here to here. It's epsilon t times this constant plus 1 minus epsilon t times this constant. And again, I'm just plugging in the definition of alpha t, and I can write it this way. So go back to the definition of alpha t. It was half ln of this thing with epsilon. Plug it in, and you'll get this expression. Okay. So this was long, but essentially we proved the theorem, right? So this is the expression for zt, and in the previous step, we showed that the error is bounded by the product of all the zt's, and therefore we proved the original theorem. Basically, what we proved is that the error of the final hypothesis can be as small as we want. The training error of the final hypothesis. Okay? Questions? So in practice, okay, so a couple of comments. I'm not going to give all the details here. So we talked about epsilon. Tech learning has 2 parameters, complexity parameters, epsilon and delta. Really, the hard one to deal with and the important one to deal with is epsilon, the error. It turns out the delta, if someone tells you, you know what, I have a learning algorithm, but my delta is just some fixed number and I don't know how to get the delta as small as I want. Essentially, by running the algorithm many times, you can get the delta to be as small as you want. The argument is a little bit more subtle than that, but basically this is what's happening. On the other hand, with epsilon, running the algorithm many times, each one of them is still going to have error epsilon. Nothing is going to help you. Yes?
Are there any general guidelines for
when do you want to stop, you mean, running the boosting? It's really a case by case. It's your preference. But in practice, I'm going to get to it. People typically run boosting at least hundreds of times, sometimes thousands of times. But again, it's really a case-by-case basis. You need to come up with some stopping criteria, but once you have it, going to work. Okay, so just to complete this argument, it's described in details in the next slide. I'm not going to give the proof here. But the idea is that boosting the confidence is easy. Doesn't need a theory, really. The important thing is what we did before, which is boosting the confidence. Okay, so as I said, boosting is a representative of a general class of ensemble methods, sort of ideas of how to take simple hypotheses and put them together in a way that improves the learning algorithm. We can talk about three representatives: boosting, bagging, random forests. And I'm going to say something about all of them. So boosting, which we describe now, we start by weighing all the training examples equally. And then we train a model, choose your favorite weak learner, some hypothesis class that you know is going to do okay. Not perfect, not very good, okay, on any sample from the data. Now notice that this is a very, very strong hypothesis, right? You basically said that for any distribution over your data, there is going to be a hypothesis that is doing better than chance, bounded away from chance, right? It's really a strong hypothesis, strong assumption. But this is really what's important here. In practice, it may not happen, right? It may not happen that for any distribution over your sample, there is a way to choose a weak hypothesis. For example, what happens if the data is noisy? Right? You could actually get contradictions in the data, and maybe this weak hypothesis assumption will not hold in practice. Nevertheless, it turns out that boosting AdaBoost is a very, very robust algorithm that can tolerate also noisy data. Even though the assumptions, the theoretical assumptions that there is a weak learner may not hold. But anyhow, we assume that we can train a model, get small error, increase weights on training cases the model gets wrong, right? So basically focus your attention or the attention of your algorithm on those examples that you got wrong previously and keep on going. And as I said, typically requires hundreds or thousands of iterations. And the final model is really carefully weighted predictions of each model. So again, this is also important. For the theory, and in fact also in practice, you don't just take the hypotheses and sum them up. You have weights. In this respect, think about what you did in homework 2. The final hypothesis that you got in homework 2 was very similar to the final hypothesis that you got here. Right? You got a weighted sum of your weak learner, your decision stumps, small decision trees. What was the difference? The alpha. So the coefficient of the hypothesis, here they are chosen one by one, right? And before, you used a global algorithm that chooses the weights for the hypotheses together. There's one other difference. What's another difference between what you get here and what you did in the second homework? Yes?
We did not use a strong learner. We don't use
You don't use a strong learner, no. You have your class of weak learners, but that's what you did also in homework 2, right? So
we fed the weak learners as teachers to a strong learner.
and the strong learner in your case was the gradient descent.
Yeah.
So what you did there is you first learn all the weak hypotheses, right? You first learn 100 trees. You fix that, and then you learn the weights. So you learn the weights globally for all the 100 trees. Here, you choose a tree, you get a weight for the tree. You choose another tree, you get a weight for this tree, and so on, which is different. So basically, the selection of the weak learners, if you want, is different. And the way you choose the alpha, the weights, is different. And in fact, here you can actually prove something about what's going to happen. You can actually try your homework 2 again, and now use the same weak learners, run boosting or other boost, see what happens. The algorithm is, in fact, very, very easy to implement, because all you have to do is you have to change the weights, right? Essentially, regenerate the distribution every round, and that's it. Okay, so that's other boost. Now, as I said, there's a lot of literature about other boost, and there are a lot of things we know about other boost. I'm going to present a few of them. So, because other boost turned out to be very successful practically, people try to analyze and understand why is it working so well. So there is a max margin perspective. I mean, we already know about margins, and you already have the intuition that large margin is good when you learn linear separators, for example, and small margin is not as good. So it turns out that boosting has a view of maximizing the margin, essentially maximizing the margin differently for easy cases and hard cases. Boosting can be viewed as a logistic regression type of algorithm. Boosting can be viewed as something that is called equalizers. So weighted proportion of the times an example is misclassified by base learner or weak learners tend to be the same for all training cases. And so these are all, let's say, good properties or interesting properties that explain one way or another why is boosting so good. There's also one downside, which is in most cases, we actually talked a little bit about it, you can take the output of a linear classifier, scale it in an easy way, and get something that you can interpret as a probability distribution. It turns out that the outcome of boosting isn't doing so well in this category, and it's not so easy to normalize it or calibrate it such that it gives a reliable probability estimate, even though there's been more work in this direction. Okay, so very quickly I want to talk about 2 other ensemble algorithms. One is called bagging. So bagging is another way of generating many versions of a simple predictors and then use them together in an aggregated way to get one stronger predictor. Essentially, you average over versions if you predict numerical outcomes, or just do plurality if it's a 0-1 or a binary classifier. So we generate multiple versions by actually generate what is called bootstrap replicates of the data, samples of the data with repetitions. Again, bagging is known to be a very good way to collect simple classifiers. And it's especially important to use it, or good, if your predictor is unstable. If when you subsample again and again, you get every time a different result. So boosting is going to reduce the variance of this predictor and eventually improve accuracy. So this is one way you can think about it. Yeah? Big decision trees. You're going to take 100 times samples of the data, learn decision trees on each one of them, and basically average the predictions. Very simple. Much simpler than boosting. Doesn't have the guarantees that boosting has, but in practice quite often works well. Random forest is another bagging algorithm. I call it here bag trees plus plus. What it does, it's not only generate samples of the data, but whenever you generate a sample of the data, you also generate a sample of the features. So typically, you have to run it a lot more times than just the simple bagging. You draw a sample of the data. Every time you draw a sample of the features, the attributes, you learn a decision tree. You're going to get 1,000 or so trees, and then you're going to do bagging, just like before. And again, this is a very, very good algorithm. So random forests is a very good way to aggregate predictors. Again, does not have the learning theory guarantees of boosting, but in practice works quite well. OK, so we talked about 3 ways to aggregate predictors. I focused about boosting because it's very good, and it has some very good theoretical guarantees. And this was #1 algorithm for us in terms of we start with some theoretical questions, and it turns out to be a good practical algorithm. Questions? OK, so next week we're going to continue with this, talking about support vector machines. And remember that there is projects due tomorrow and an exam in about a week and a half. Hi.
In the ad host, for the disadvantage, I don't understand the probability things. There's disadvantage for the ad host.
Oh, so, okay, just 1 second. Many times when you have a